Hey, this is Mel Strong, and in this lecture, we're going to be talking about some of the major water projects of the southwestern United States. So the big picture here is that if we look at a map of precipitation for the US, and we've seen this map before, there's this big blob of orange and red colors here in the southwest. And if we just kind of drew a circle, kind of a right through around there, there's about 40 million people living in the driest part of the country. And today's lecture is about how that is possible. So this is more of a history and maybe a little bit of politics lecture and less on science. So before we start, just imagine the following. Imagine if somebody came to you and said, you can continue living here in Albuquerque or Arizona or wherever you live, but the deal is you can only have the water that fell from the sky. Okay? How easy would it be to live here? I mean, it would be pretty tough to carve out a living if you could only use the water that actually fell as precipitation, right? And yet we have this system that you just turn on the faucet, boom, water comes out. It's a miracle. Question is, how did all that come to be? How does it work? And when did it happen? And for most of the things we're talking about today, all of this happened before any of us were born. Okay, this is a system that was started over 100 years ago. People are still working on it, and we completely depend on this to live in the driest part of the country. So we're going to start our story in Los Angeles. And in fact, the big motivating factor behind what we're going to be talking about is population growth. So if you go back to 1900, okay, these are the state populations, right? So New Mexico has under 200,000 people in the whole state. California has 1.5 million. And if you project forward, when this paper came out, it was 2007. So a little over 100 years later, you can see that states like California, 36 million. So their population didn't just double, it didn't quadruple, it wasn't even 10 times, it went up 20 times, right? And you see that in a lot of these states, that the population, pretty much all these states, the populations increased by way more than 10 times in 100 years. So you've got all these people living in an area that's very, very dry. And so we're going to actually start our story in Los Angeles, where in the late 1800s, there was just a few thousand people living there. And at the time, there was a bunch of real estate investors, and they bought up a bunch of land around Los Angeles. And they thought, here's what we're going to do. We're going to sell this place as a great place to live. And so they went up to San Francisco. And San Francisco at the time was the biggest city along the West Coast. It was this major port city. We just had the gold rush and all that. And so these real estate investors came in and they said, listen, aren't you guys tired of this cold, crappy, foggy San Francisco weather? Well, let me tell you about a great place to live where it's sunny almost every day. It's called Los Angeles, and we've got some property to sell you. And this plan actually worked. In about 30 years, LA goes from being a few thousand people to over 100,000 people that move there. At the same time, early 1900s, we start to get the very first movies. Now today, everybody knows where Hollywood is. Hollywood's in Southern California. That's for a long time has been the movie capital of the world. Well, why didn't it start there, right? Like of all the places in the world or in the United States, why did Hollywood get set up there? Okay, so if you go back and you watch an old-timey movie, like an old silent movie with an indoor scene like this one, so it looks like they're filming this indoors, but actually there's no roof on this. This is natural light coming in. These old movies, they didn't have artificial lighting yet, so the only way they could film is if you had a sunny day. So they needed a place to build their studios where they could have as much natural light as possible so they could film all the time. And so this area right down in here is a place that is sunny almost every day of the year. Why is that? Review question. Why is it so dry? Why is it so sunny over here? Well, a big reason is our old friend, the Pacific subtropical high, right? So the Pacific subtropical high is responsible for why Hollywood is where it is today, because that constant sinking air keeps the sky clear, allowed those old-timey movies to have natural lighting. Okay, so that's how it all got started, Pacific subtropical high. All right, so late 1800s, we go from a few thousand people to over 100,000 people. And at first, the people that show up and live in this area are getting water out of the local river. So there's something called the LA River with a few creeks that feed it. Okay, so this is the map of it today. And that works for a little while if you have a few thousand people. But by the time you get to 100,000, that's not enough water to go around. And so they started to drill wells. So we're going to talk a little bit here about groundwater for a minute. So below the ground, there exists a body of water in most places, and this water becomes replenished in the winter. So in this diagram, you've got some topography, and this blue represents water that has soaked in from above. So usually what happens in our part of the world, during the wet season, like the winter along the west coast, rain will fall and it will soak down into the ground, and then what most people don't realize is that the groundwater is actually moving. Now, the water table itself is this surface. That's called the water table. And anytime you have a river, that's just where the water table comes out onto the surface. So here's an idea. Here's a little diagram of this. So you get what are called recharge areas. These are areas where the precipitation is added, soaks down, and then it's actually on its way, it's moving downhill. The water underneath the ground is moving downhill, and ultimately it's headed to the ocean. Okay, now this shows it moving kind of left and right towards these rivers, but it's also moving either in or out of the slide, depending on which way is towards the ocean. So what that means is if you drill down far enough, you could get groundwater like this, trying to show a well that they didn't drill far enough, so it's dry. Here's one where some water is kind of piled up here on this barrier, so that one they're getting water out of. Point is, for most places in the world, you drill down, you'll probably eventually find some water. Okay, you just have to drill deep enough. So they do this in Los Angeles, and this is a map of 200 large wells that are drilled in the Los Angeles area. So these are not like in your backyard wells. These are wells that are big enough to supply water to a whole neighborhood. Okay, so they pump a lot of water out of the ground. Well, there's a problem when you start to pump a lot of water out of the ground. So here's the water table. Okay, so here's some wells, and as they're pumping water out of the ground, you can see that the water table lowers a little bit by each one of these wells. That's sometimes called a cone of depression. So here they've put in this, this is trying to show they put in this new well here, and they're going to pump a lot. And so it pulls down the water table as they remove water out of this big high capacity well. And these guys, their well went dry now because the water table has been lowered. So basically Mother Nature cannot replenish the groundwater as fast as the humans are pulling it out. Okay, so back to Los Angeles. When they start everybody starts putting in wells. At first, people are able to pull water out of the ground. But as more and more people do that, pretty soon the water table all starts to go down, and people's wells start to go dry, and they have to re-drill those wells deeper and deeper. So here is a little graph of depth to the water table. Okay, so now this only starts in 1935, and our story is starting back in the late 1800s, and we don't really have any data for that. But just from 1935 to 1960, what this is, it says groundwater elevation, feet from sea level. So remember, LA is pretty close to sea level, okay? So what this means is, back then, if you drill down till it was 60 feet above sea level, you hit groundwater, right? But then, if you go ahead to 1945, you had to drill down until it was 40 feet above sea level. And then you had to drill down to sea level. And then you had to drill down to 60 feet below sea level. So what's happening from 1940 to 1960, you see this blue line here, people were having to drill deeper and deeper and deeper holes just to get to the groundwater because everybody was pumping it out faster than Mother Nature could replenish it. So on average, the groundwater was dropping 8 feet per year. Okay. Well, they have an additional problem in that so here's our little cone of depression here. If you pump down the water table and you happen to live close to the ocean, then seawater will come in and take the place of the fresh water. So normally, before the well was drilled, there was fresh water that was coming down from the Sierra Nevadas in the case of LA and migrating on this diagram from left to right and then out into the ocean. So you had constant fresh water moving underground. But once you start pumping it out and you start removing the groundwater, then salty water will come back in and replace it. And then people start getting salt in their groundwater. So there's a limit as to how much groundwater the people in Los Angeles could pump out before it started to go salty. Okay, so to recap, they took water out of the river, and that worked for a little while. Then they started to pump wells. That worked for a little while. But they start to run out of water and realize that this groundwater solution is only temporary. You can't keep pumping water out of the ground. Okay, so by 1900, again, we're about 100,000 people. They're already running into trouble. And they don't have enough well water. They don't have enough river water. What are they going to do? And all these people have moved here, right? So this whole campaign to get people to move here in Hollywood and all that's getting going. And it's clear that people want to live in Los Angeles, but there's not enough water. So here on this map, here's LA. And if you're in my class, you had to do this project trying to find some things on the map. And one of the things that I asked you to find was something called Owens Lake. Okay. And I have Owens Lake right up here with a little dashed line. So this is lake that sits up here. So they're thinking about what to do. And someone said, well, here's a crazy idea. So the reason this lake exists, this is all desert, by the way. This is all desert. But there's a lake up here in the desert. And the reason that lake is there is because there's these little streams that come out of the mountains, out of the Sierras, and they drain down into Owens Lake. So what if we captured those streams, and instead of allowing the streams to fill the lake, we laid this giant pipe all the way from this lake all the way to Los Angeles, and we'll just take that stream water and we'll redirect it to LA. Okay, it sounds crazy, but that's what they did. And so they decided this is late 1800s, early 1900s when they're thinking about this. They're going to start this giant project to take water that should be going into Owens Lake and bring it all the way across the desert to Los Angeles. So we don't have a lot of pictures of Owens Lake from back then. This is one of them. So here you can see we've got the Sierras here in the background. You see this body of water here. Okay, this is about 1900. There's some mining town or something here up in the foreground here. And they're going to form what's called the LA aqueduct. That is this red line that runs from Owens Lake all the way down to Los Angeles. So again, if you're one of my students, I have put up a map with all the things I'm showing you. Okay, it's all on Learn, so you can go and see this, print them out, or whatever you want to do. So the LA aqueduct, huge project. They started this thing in 1908. 223 miles of pipe were laid to take water from Owens Lake all the way to LA. They finished it in 1913. Realized at the time what they're dealing with in terms of, cars hadn't really been invented. I mean, a little bit, but not so much. Pretty much everything is with mule teams. There's no electricity. There's no tractors, and they're doing this big project, right? So it was a pretty significant thing to build. So here is another old picture. Again, there's Owens Lake in the background, and here's this concrete conduit. That's the LA aqueduct. So what's going to flow in the bottom of this ditch, and here it kind of looks like the arroyos that we have around here in Albuquerque, is water that's supposed to be flowing into the lake, but instead it's headed south. Then from this concrete ditch, this is what it looks like today. Okay, so that's water that's on its way to LA. It will go into these pipes. So these are the pieces that were, these big pieces, they were made in Germany and brought in. You can still see them today. There they are going across the desert floor. They go up mountains. Oops. They go down mountains. They go across the desert, through towns, across freeways, and then eventually that water comes down into the LA basin. So this thing right here, it's like a bunch of little stairs. That's water coming down into Los Angeles. So the guy that was in charge of this is William Mulholland. And Mulholland is this kind of famous name in LA. There's Mulholland Drive, and you'll hear songs and movies referencing Mulholland. So that guy was in charge of this project. And in the 1980s, there was a pretty famous book written called Cadillac Desert. And it goes into detail about this and some of the other water projects we're talking about. And PBS in the mid-90s put out this big mini-series on Cadillac Desert. I think it was like 9 hours long, something like that. And for whatever reason, they never released it as an actual video that you can watch today. So the only parts of it that exist are parts that were recorded on VCRs back in the 90s and then uploaded to YouTube. So the quality is really, really poor. And I'm just going to show you a couple minutes of a clip of them building the LA aqueduct. So again, I apologize. The quality is pretty poor. It's the only thing we really have today. So I'm going to show that real quick here.
It was a great drama. It was a great epic drama, the building of that aqueduct. You had mule teams and you had men. They were working in desert heats, arid conditions. Water was a problem. Ironically enough, here on this giant water project, they had to worry about adequate water for the working stock and the men.
It can be almost freezing at night and then 110 degrees in the daytime practically. Mulholland was there all the time.
Chief Engineer Mulholland had no formal training in civil engineering. He had, in fact, never graduated from grade school.
The automobile had barely been invented. Clipper ships were still sailing the seas. And this was an engineering project the likes of which the world had really never seen before.
Mulholland ordered 12-foot steel pipe forged in Germany and shipped around the Horn. 100,000 men and women worked on the aqueduct, but never more than a few thousand at a time because the exhausting and dangerous work kept turnover so high. They had been farmhands, cowboys, and hard rock miners, but now they were city employees, civil servants like the chief himself. With no air conditioning, no refrigeration, no hard hats, in 110-degree heat, they crossed the Mojave in 5 years with a pipe big enough to hold a locomotive.
This was, an aqueduct that would have reached all the way across Massachusetts and then almost all the way back through a desert with mountains. What they were really building was the world's longest garden hose.
Surveyors said they could build the aqueduct simply by following the trail of whiskey bottles Mulholland and Eaton had thrown off the back of their buckboard in 1904. In the end, the chief and his lieutenants finished the job under budget and ahead of schedule. William Mulholland built his original aqueduct so well that to this day it still carries the Owens River to the people of Los Angeles.
The phrase Grandpa's aqueduct were among my first words. The day of the dedication of the aqueduct was, without a doubt, the high point of my grandfather's life.
A crowd of 30 to 40,000
Los Angelenos had gathered at the base of the spillway. There was a formal program, but once the water spilled down the cascade, the formal program was abandoned because thousands of people rushed with their tin cups to drink the water. When the water came cascading down there, Mulholland, who was really exhausted at the time, gave what I think is the most concise dedication speech in history. He unfurled an American flag, he turned to the water, and he said, "There it is. Take it."
Based on Mulholland's predictions, it was 4 times more water than Los Angeles could use.
So you probably figured out that was Mulholland's granddaughter in that movie. The other thing I wanted you to pay attention to is in the opening ceremony, they release the water, it comes down the spillway and all that. And Mulholland says this is 4 times the amount of water that Los Angeles is ever going to need. So keep that in mind, okay? So they take the waters that are supposed to be going into Owens Lake, they redirect them to LA. What happens to the lake? Dries up, okay? So if you're one of my students and you're trying to find Owens Lake on the map, you may have had some trouble because the lake no longer exists. Here we can see where it was. This big brown spot used to be full of water, okay? And notice what's around, right? This is pretty dry. Sagebrush, we're in a pretty dry area. And you can see from space where the lake used to be. So this, again, kind of light colored spot right there. And this lake was pretty important to the environment because when you have a lake sitting out here in the desert, it's super important for all kinds of organisms to survive out there. And that includes those that live around the lake, plus a lot of the migratory animals that stop there to refuel and what have you before they move on. So, a lot of migratory birds, for example, used to stop at Owens Lake on their way, one way or the other, and now they can't do that because that lake is no longer there. So this is, there was a complete collapse of the ecosystem from the disappearance of Lake Owens. And you'll notice here that this is what it looks like today. These are all mostly kind of salts that were left behind after the lake dried up. See this kind of white, if you walk on this kind of white, crunchy texture to it. And when the wind blows, it blows up dust from this lake bed. Now, if you remember a few lectures ago on air pollution, we said that particulate matter, PM, is one of the regulated pollutants that we keep track of in this country from the Clean Air Act. So in the 80s, the EPA goes to the city of Los Angeles and says, see all this PM? That's your guys' fault, okay? Because you caused this lake to dry up, and now the wind's blowing that dust, and you're responsible. So LA says, okay, here's what we're going to do. We will drill a well, and we're going to install sprinklers on the bottom of what used to be the lake bed. So they're irrigating the bottom of the dried up lake bed to prevent the dust from blowing all this PM up into the air. Okay, that's their solution. There's been a few attempts to try to reintroduce a little bit of water into the lake to try to get some of the wildlife to come back. You can see this little sector here has a little bit of water in it. When I say a little bit, it's literally just a few inches deep, right? So all the white area, that's the salty spots again. So a little bit, but not enough to really bring it back to anywhere where in the status it used to be. Well, that works for a while. And we get to 1930, and the population of LA has increased tenfold again to over 1 million people. And oh, look, we're out of water. So no, it wasn't 4 times the amount of water that LA would need. 30 years or so later, they're already out of water. So what are they going to do? So they look around on the map, and they said, well, here's a crazy idea. Way up north, there's another lake called Mono Lake. How about we do this same game plan and we extend our aqueduct up here and take the water that's supposed to be going into Mono Lake. So this is the plan. And what they do is they extend that aqueduct that went up to Owens Lake, and they continue on this red line here. And in 1941, they get all the way to Mono Lake, and they start taking the waters that are supposed to be going into Mono Lake. Well, this is what Mono Lake looks like today. Now, it has not dried up yet, and we'll talk about why in a second. But you can see the lake used to be a lot bigger. You can see where the old shorelines used to be out here. These are islands that used to be underwater. Okay, so it used to be about twice as big as it is today. Well, it was drying up. And in fact, by the time you get to about 1960 or so, the volume of the lake had halved and the salinity had doubled. So in this body of water, it's twice as salty as it was before, and animals are having trouble surviving. Things are starting to die out. And it looks like, to everybody, that the whole ecosystem is collapsing just like Owens Lake did, right? So, a bunch of citizens got together and they decided, before this lake completely dries up like Owens Lake, we're going to fight this in court. And they got together and they sued City of Los Angeles. And there was, in the 1970s, there was something called the Mono Lake Committee. Citizens and some scientists got together and started these lawsuits to try to slow the destruction of Mono Lake. And it goes to court, and after several years, they decided that, they said, okay, the court decision essentially was, if I go back here, LA is allowed to take water, but they cannot allow the lake to go below a certain level, which is the level you see here in this picture. So it's not going to get any deeper, it's not going to get any fuller, but it's also not supposed to go down anymore. Okay, so that's the ruling that came out. And again, this was 70s and 80s when this happens. And so that was a result of citizens just getting together and suing and trying to prevent this whole ecosystem from collapsing in the same way that Owens Lake did. Okay, well, by the time we get to 1960, the population has now doubled since 1930, when they started to go to Mono Lake. And again, they're out of water, right? So another solution they come up with is to double up the aqueduct. And so there's a second LA aqueduct that goes parallel to the first one. So on this picture, this is the first one. That pipe right there, that's the second one. Okay, over here, there's the first one, there's the second one. So they just have two pipes right next to each other going right up to Lake Owens so that they can take twice as much water. So from LA up to Owens Lake, there's actually two pipes next to each other. And then there's only one that goes the rest of the way to Mono Lake. Okay, well, LA's out of water still after going to Owens Lake, after going to Mono Lake, after doubling up the aqueducts, after getting the water out of the rivers, after getting the well water. So they start looking around and they're like, well, you know what? There's a nice little river over here called the Colorado. Sure would be nice if we could take some water out of that. So this brings up an important point, which is who legally is able to take water out of a river if the river is shared between several states. So this is the Colorado River. Starts in Colorado up here, off the map actually. Comes down through, from Colorado through Utah, through Arizona. It's on the border between Arizona and Nevada. It's also on the border between Arizona and California. Goes to Mexico, goes out into the Gulf of California. So, here's the problem. Let's say Arizona says, okay, so in case you didn't know, this is the Grand Canyon right here, right? So what's preventing Arizona from saying, we're going to put in the giant dam right here, and we're going to block the water. We're going to make this gigantic, we're going to fill the whole Grand Canyon full of water, and we're just going to keep it. And nobody downstream is going to get any of it. So none of it goes to California. So what's preventing Arizona from doing that? Because technically any state along the river here could put up some kind of dam, and everybody downstream would suffer, right? So states realized they got to figure something out. This is about 100 years ago when they're thinking about this. So what they decide is that if you are part of what's called the Colorado River watershed, you are entitled to a portion of the Colorado River water. Now, what is a watershed? So all of these little red lines are little rivers and little creeks that ultimately go into the Colorado River, right? So if you are a raindrop and you fall and you land in this red zone anywhere here, you'll end up in the Colorado River. That's the watershed, okay? This whole area are all these rivers that ultimately feed the Colorado River. We're going to zoom in a little bit here. So the Colorado River itself doesn't even go through New Mexico, for example, right? It's over here, okay, and it goes this way. But here we are, here's New Mexico, and notice that we have some of those little red lines over here. So we have a bunch of little creeks that ultimately flow to the west and end up in the Colorado River. So what this means is, states like ours, we don't have the Colorado River, but because our little streams feed the Colorado River, we are legally entitled to a portion of the Colorado River water, as are all the states that have a little bit of these red lines, okay? Including California. Now, California has a pretty tiny, measly amount of watershed, right? It's just like a couple little chunks of red line here. That's the only thing that feeds the Colorado River. And they're in the desert anyway, so that's not a lot of water. But technically, they're allowed to have some of the Colorado River water. Well, they decided that what they're going to do is they're going to split up all of these states into what we call upper basin states and lower basin states. So these are all states that are part of that watershed. They all legally get some water, okay? But they're going to subdivide, and again, here's that little bit of California here, but they're going to subdivide the Colorado River water up between all of the states that have part of this either upper basin or lower basin shading. Okay, so all these states get something. So in 1922, a bunch of politicians get together to hash out what's called the Colorado River Compact. The Colorado River Compact is like a treaty among, instead of a treaty among nations, is a treaty among states. And they decide, okay, we're going to figure out who gets what. Now, is it evenly divided based on the watershed? No. Who gets the most amount of water? California gets the biggest amount of water, even though they have a very tiny portion of the watershed, but they had the biggest population, so they had most political weight when this was all decided. There's a unit here, capital M, capital AFY. That stands for million acre feet per year. What does that mean? An acre? Imagine a football field, okay? Now imagine a football field that you flood with 12 inches of water, a foot. So now you've got a flooded football field with a foot of water on it. That's called an acre foot of water. Now imagine, you can't really, but a million of those. That's a million acre feet. Okay, so what this is saying is that Colorado, you get 3.86 million acre feet per year. And Nevada, you get 0.3 million acre feet per year. So this was all hashed out in 1922. Now, how did they come up with these numbers? Well, what they did is they went and they surveyed the Colorado River, and they wanted to figure out how much water does the Colorado River deliver. Okay, so in 1922, they go out with a bunch of gauges and they're measuring how much flow is coming down the Colorado. And then they look at that number and they divide it up between all these states. Well, we now know there was a problem with that. 1922 was an unusually wet year. And we've had very few years since then as wet as 1922. So all of these numbers are based on an unusually wet year, which means that today, on a normal drier year, that these numbers cannot be obtained. But there's a treaty in 1922 that says each state gets to have this much water. So right away, out of the gate, we got a problem because the states are now fighting each other that they're not getting their fair share of water. We've been in the drought, we'll talk about this later, for many years in the Southwest, which means that these numbers are much lower than, much lower than they were in 1922. So this is a cause for friction in the Southwest because everybody wants the water, they're legally entitled to it, but there's just not enough to go around. Okay, so once that's hashed out in 1922, and everybody says, okay, you get this much, you get this much, you get this much, now people can start building dams and taking water out of the Colorado River. Okay, so again, if you're one of my students, on your map I had you find some of these dams and outline some of these reservoirs. And again, I have put a map on Learn with these features on there. One of the very first dams, major dams that gets built, is Hoover Dam, okay, which is now next to modern day Las Vegas. This is what Hoover Dam looks like before they built it. At the site of Hoover Dam, you see how these there's a narrow kind of a V shape here. Whenever they're trying to build a dam, they're looking for a spot where the river narrows because it makes it easier to build across this. So they're going to fill up this V in this canyon with concrete, and that's going to be Hoover Dam. So here they are building it. This is in the 30s, kind of a Depression era project, puts a lot of people to work. And here's what it looks like when it's done. So this is the Colorado River. Now it's stuck behind this wall. That's Hoover Dam. And notice these towers here. Okay, and I'm going to show you another picture referencing these towers in a second. So they build this dam in 1935, and the Colorado River comes up behind it and gets stuck and starts to fill up with water. And that's going to become Lake Mead. So here we are filling up the dam. Here's those 4 towers again. And here's what it looks like when it's full. There's the 4 towers. Well, one's off the picture. This is one of the few times that Lake Mead was full. In fact, it's flowing over this overspill area right here. This is in the 1980s, an unusually wet time, turns out. It almost never, ever looks like this. Okay, this is what it looks like when Lake Mead is actually full. So the lake, you realize, was formed by just flooding the river that was behind the dam, right? So the river was coming along doing its own thing. We fill this up with concrete, and now the water starts to build up behind it. So this is going to make a lake, but it's a weird lake. Like normally, if you tell somebody I'm going to go up to a lake, they're kind of visualizing usually something kind of roundish, but we're making artificial lakes here by putting a dam up, and so we're flooding what used to be a river, and it just floods it upstream and makes a very unusual shaped lake. And here you can see, notice how dry this is. Okay, if you haven't been to Las Vegas, what's it like? This is temperatures routinely over 100 degrees in the summer. The relative humidity is a few percent routinely. Here's Lake Mead winding out into the distance, right? So this was a river valley, but now it's full of water. Look how dry it is, right? Nothing growing here at all. What's the evaporation rate, do you think? You got temperatures over 100 degrees routinely, relative humidity, single percent, big surface area, right? Big surface area. You're losing a lot of water to evaporation. And so you're in this area that's super dry. You're building dams to store water because you want water to live where it's super dry, but you're also losing a lot of it through evaporation. Well, once Lake Mead is built, once Hoover Dam is built and the Lake Mead is there, Las Vegas was this little tiny nothing in 1930. This is the whole city, but now you've got a source of water. The dam is producing electricity, so you got a source of electricity. Prohibition ends, and also we had a moratorium on gambling. Most people don't know this, but back Prohibition days, you couldn't gamble either. And so all those things, Prohibition ends, gambling is legal, you got a source of water, you got electricity. Las Vegas just explodes, right? And so water use in Las Vegas explodes along with it. So here's a population, and this is in thousands, so 1,000 is a million, right? So the population is going up, that's these dots, right? And then as it goes up, the water consumption goes up too in millions of gallons per day. Now this is coming out of the groundwater there. So they're using groundwater where they can. They're using water out of Lake Mead because it's there and they're legally entitled to some of it. But of course, the water is very much needed for very important things like the Bellagio fountains, right? You've got to have that. Do you think there's any evaporation going on here? You're throwing little droplets of water up into 100+ degree air with relative humidities in single digits. How much water do you suppose they're losing here just in evaporation? Or maybe you need to use that water for other very important things like golf courses. And I especially like this picture to show the stark contrast between the super dry desert here in the background and the heavily irrigated golf course right next to it. So that's where a lot of this water ends up going out of the Colorado River. So that is Hoover Dam and Lake Mead, right? We go upstream, we go through the Grand Canyon, go through the Grand Canyon, go through the Grand Canyon, and we get up here, and there's another dam called the Glen Canyon Dam. And behind the Glen Canyon Dam is Lake Powell. So same idea. The Colorado River was coming through here, minding its own business. We put up this big dam. We block it. The river canyon floods. And so now we have this big, funny, windy-looking lake called Lake Powell, which is just a flooded river canyon. So it's this weird, windy-looking thing. Well, Glen Canyon Dam was built at a time when this was in the 50s, and there was actually a significant amount of protest around building this dam. And the reason for that is because Glen Canyon itself was a canyon that people actually liked to visit. It was kind of an extension of the Grand Canyon. So the picture on the right is what it looked like before they flooded it. So all this water is flooding this canyon, right? There's water up to the top of this canyon, at least there is in this picture. This is what it looked like. This is what they flooded. And there's a significant number of people who thought this is a really bad idea because this is a really beautiful place. It's one of the nicest places in the world to go. You can go rafting, you can go fishing, you can go camping, and we don't want to lose this. We don't want to flood it. Like, it just doesn't make any sense. And people fought this. And so these pictures I'm showing you are what it looked like before the dam was built. So these are all pictures from the 1950s or before. So you can see it's a pretty nice place, right? I mean, it kind of reminds you of the Grand Canyon. It's similar to the Grand Canyon, except it's now all underwater. People used to go rafting, slot canyons, the whole thing. Here they are starting to build the dam. The dam's going to go right here. Okay, so that canyon behind us, that's going to be filled with water. Now, an interesting point to this story is that because we've had a lot of drought in the last 20 years in the Southwest, that Lake Powell is no longer up to the top like I showed you in those earlier pictures. And as the lake has been receding, it's revealing some of the original canyon. Not like it used to be, but you're starting to actually see a canyon again. So that's an example where some groups got together. They fought the formation of a dam. Didn't work out. This dam was still built. There are still groups today fighting to get the dam removed. Okay, so this is, I don't think they have a very good chance of this, but people are still trying to get that dam removed. Worth pointing out that there was also another dam that was going to go up somewhere around in here, kind of in the middle of between Hoover Dam and Glen Canyon Dam. And that one was also fought, and that one was dropped. So we could have had another dam that would have flooded a good portion of the Grand Canyon. And our predecessors, thankfully, I think, fought that and prevented that. So we actually have the Grand Canyon as it is today. So we're going to talk a little bit about some of the problems of putting dams on a river like the Colorado. And let's just imagine that we had, think about a river going down a slope, and the water's coming down, doing what rivers do, and then what I'm going to do is put up this dam, and the water is going to accumulate behind the dam, fill up, and produce a reservoir, right? And then I'm going to have some way of releasing a little bit of water out the bottom that continues on down the stream, right? So that's the system that we have in place. So what's the problem with that? So one of the biggest problems is if you are an organism like a fish and you are trying to, say, get from here to here, you've got a problem because you've got this big dam structure in the way, okay? And some fish really need to migrate. That's part of their natural life cycle. So salmon are a classic example. So salmon start their life out up in a very shallow, slow-moving creek, and they lay eggs, okay? And then the parents die off, and the eggs hatch in the spring, and you got little baby salmon, little bitty guys, and they grow in this river, again, a very slow-moving river usually, for a couple years. And then when they get big enough, they migrate downstream, and they head towards the ocean. So they come out into the ocean, and they'll spend years out in the ocean, swimming around doing whatever salmon do. Late in life, they come back to the same river that they came out of, and we don't know how they do this. Every river must have a unique chemical signature that they can detect somehow. But they'll go back and find the same river they came from. And they'll go upstream. So they got to go up the river now. And so whenever you see pictures of salmon jumping, trying to get up little rapids or waterfalls, they're trying to get back to the place where they were born. And they'll go all the way back to the place where they were born. They find a mate. They lay eggs. And then they die. And the whole process starts again, right? So this is what salmon do. So if you put up a dam in the middle of that whole process, you've just prevented this whole life cycle from taking place, right? Which is a major bummer if you're a salmon trying to make a living. Now, there's a few things that have been done to try to mitigate this, namely something called fish ladders. So the dam is over here, okay? And so just to orient you, so there's a stream that would be kind of behind us. So before the dam was in place, the salmon would come this way, and they just go upstream to where, this concrete would not have been there originally, and they just go up to where they need to go. But now this concrete's here. So what they have is you can see these look like little steps. That's a fish ladder. And so the salmon figure out that there's water coming down this way, so they instinctively go up. And they go up all the way through these steps, up, and then they jump off and they land on the other side of the dam. That's a fish ladder. And there are places where you can actually kind of watch this in action. So here's a salmon trying to jump the stairs of a fish ladder, and you can see a bunch of them trying to get up the fish ladder. So it kind of works. Definitely some salmon are able to return home through fish ladders and keep going. But a big problem you have is with oxygenation. So back in my picture of this dam here, if this fills with water, the water down here is very stagnant, okay? And because it's very stagnant, it has very low oxygen. And dams are designed to release water out of the bottom. So the water that comes out of the bottom of this dam also has little oxygen. Now that's not true with the water that goes into the dam, right? You've got rapids, you've got fast-moving water, gurgling, bubbling, there's a lot of oxygen in there. It fills up this reservoir and stagnates, and that low oxygen water comes out, goes downstream. So any animals that are down here are stuck in this water that has relatively low oxygen. A lot of them don't like that. Sometimes your deoxygenation can get to the point that fish actually die. So this is, here we're in the dam. Okay, so now we're talking about fish living in this part, in the reservoir, and the oxygen level got so low that a whole bunch of fish died. And it usually happens overnight. So during the day, there's some photosynthesis that's helping reoxygenate the water, but then respiration is happening all night long, and that's when your oxygen level goes down. So this can happen if you don't have enough oxygen in your reservoirs. The deep water also is colder. So this water that comes out down here not only is low oxygen, but it's cold. And again, we're thinking about the animals that lived in the water before the dam was built. They're used to pretty shallow, pretty fast moving water, which is oxygenated and warmer than what's coming out of the dam, right? So what's coming out of the dam now is colder and has less oxygen, and a lot of the animals just can't survive in that. The other weird thing is that this water up here at the very top of the dam is actually warmer than it normally is. It's stagnant. There's not a lot of mixing. The sun's up every day, and it's warming the top layer of that water. And so, for example, you take something like this. Glen Canyon Dam we've seen this picture before. It's Glen Canyon Dam in Lake Powell, and this used to be a fast-moving river, which is now just pretty stagnant. And you go from the water that was in the Glen Canyon Dam, in Glen Canyon before the dam, and you can see it's kind of choppy and it's aerated and cooler temperature compared to the surface of what's on Lake Powell today. And see all this green stuff? That's algae. And algae is happy in this environment where there's not a lot of motion and it's relatively warm, because we're talking about water at the top of the lake now, not the bottom. The bottom's cold, but the top is warm. So this is what it looks like now. This is what, when we built that dam, Glen Canyon Dam, we transformed this kind of water to this kind of water. And that's, again, because it's stagnant and it's really warm along the surface. They prevent sediment from moving downstream. Okay, so if you've got sediment coming down normally, it's being washed down, and it heads out to the ocean, but what happens is it starts to pile up behind the dam. Okay, now why would that be important? If you look at the mouth of a normal river, so here comes a river dumping out into the ocean, and you can see all this mud, and you can see in the water that it has this browner color. This is sediment, and this sediment is actually really needed by a lot of the ecosystems downstream from where the dam is built. So here's a couple of examples. So here's our dam, and here's the sediments that are accumulated behind the dam, and the water is coming out. So at first, the water's flowing where it used to, okay? But because we are keeping the sediment trapped back here, that river will start to cut down into the surrounding rock, and there's no sediment to come back and rebuild anything. So what happens is the river starts actually cutting downward into the landscape. Now, when the river cuts down, the other thing that happens is the water table also goes down with it. So let's say in this scenario, we had a river that was kind of near the surface here, and we had some trees. Let's just draw here. Let's say we've got some trees growing kind of by the river, and they have a root system. Okay, the root system comes down like this. Okay, now as the river cuts down, right, as the river cuts down into the surrounding country, eventually the water table goes down with it, and the roots, which used to be able to get groundwater from the surrounding river, now are dry because the river has now cut down below where the root systems are. Okay, so I'm exaggerating this to illustrate a point, but if the sediment is blocked, then the river cuts down, water table drops with it, and eventually it can drop far enough down that some vegetation downstream will eventually die because it can't get water. So therefore, if you block sediment, then the river downstream will erode away. Okay, so we just talked about that. Rivers downstream cut down deeper than they used to. Okay, so we talked about that. And the water table lowers downstream and vegetation can die. Okay, so those things can happen by just blocking the sediments from going downstream. Now, everything we've been talking about is how the natural animals and plant life don't like these changes. They don't like the water that might be colder or has less oxygen or whatever. But there's something that will, right? If you set up an artificial lake, essentially, and you change the temperature and you change the oxygen and do all these things, there's some other organism that's actually going to thrive in that. And they're going to get into these lakes and they're going to do well. And you're going to have an invasive species problem on your hands. So by building dams and building these artificial reservoirs, we're setting up situations, environments for invasive species to come in and wreak havoc on the natural ecosystem. If you were in my class, you had to identify a few major dams on a few rivers, but realize there's a lot more than what the ones that we're talking about here. So on the map that we're using in my class, which again is on Learn or on my website, here's a number of dams in various states, which means that there's over 5,000 dams that are on that map. I just had you identify a handful of them. They're all different sizes, right? So they're not all as big as Hoover Dam. Some of them, they're just a little structure just right underneath the water that you wouldn't even notice if you're standing there looking at it. And some are these giant, concrete structures. So pretty much every water system, river, creek, whatever you want to call it, is under control now. That we have everything pretty much dammed up, and we as humans control when the rivers flow, when they don't flow, when they're allowed to flood, etc. There's very few waterways left, in fact, in the United States in general, that are actually naturally flowing anymore. So one thing that is on your map is something called the Continental Divide. And the Continental Divide here is shown as the margin of these two areas, the lower basin and upper basin. What's the Continental Divide? That's supposed to be the place in the country where if you're a raindrop and you fall on the east side of the Continental Divide, you will eventually flow to the east and into the Atlantic Ocean or maybe the Gulf of Mexico. If you're a raindrop and you fall on this side of the Continental Divide, you flow to the west and you end up in the Pacific or you end up in the Gulf of California. Okay, that's the Continental Divide. Well, the Continental Divide is a natural boundary between where water drains, right? But there are several instances where humans would like to take water from one side of the Continental Divide and bring it over to the other. And Colorado is one of those places. So Colorado is entitled to a portion of the Colorado River water. That's part of the 1922 agreement. Where are all the people in Colorado? Well, Denver's over here, and the rivers are over here. Now, before Denver, they still wanted water over here for agricultural reasons, right? There's a lot of reasons you might want to have water over here, but it's draining the wrong way. So what do? Well, what they decided to do is they decided to drill tunnels through the mountains in something called a trans-mountain diversion. Trans-mountain diversion means the natural flow of the water is it's going to go on one side of the mountain, but what we're going to do is we're going to put in some tunnels and we're going to redirect it through the other side. Okay, so if you go in Colorado, you'll find some of these diversion tunnels, and it's water just literally going through a tunnel and through a mountain coming out the other side. This is water that's supposed to go in the Colorado River. Colorado decided that what they wanted to do with their Colorado River water is direct it through underground through the mountains and out the other side, over towards in direction of Denver. Okay, so all of those things are happening along the Colorado River. We're building dams, we got trans-mountain diversions. Let's go back to our friends in California. Remember, they were running out of water over and over and over, and they were looking towards the Colorado. And after 1922, that treaty is passed, they're now allowed to take water from the Colorado. And so there's a little dam that's on your map called Parker Dam, and it backs up the Colorado into this lake called Lake Havasu. And if you go there, this is what it looks like. Okay, so there's Lake Havasu in the back. And you notice there's water that kind of goes off to the left here. That goes into a canal that's called the Colorado Aqueduct. And it takes water from the Colorado River across the desert and into Los Angeles. This is what it looks like. So it's a concrete lined ditch for the most part, and the water goes across the desert and into modern day Los Angeles. As it makes its way there, there are opportunities for farmers to get water out of that. And this is one of the early promotional traveling exhibits for the water that's coming to Los Angeles. And this helped build up the agricultural areas around there. Well, if there's a worse place to build a city than Las Vegas, it might be Phoenix. Okay, so it's just as hot as Las Vegas or hotter. It's far away from any bodies of water, out in the middle of Arizona. And so Phoenix is also having its own water difficulties. And just like in California and all these places we're talking about, they've been running out of groundwater. So this is not a great graphic, but it says approximate decline in groundwater levels from 1940 to 1995. So this is, we're looking at feet, so minus 150, minus 200, minus 50. That's how far the groundwater level has dropped. So what that means is if you lived, say, in the bullseye, you have to drill down 200 feet deeper in 1995 to hit water than you did in 1940. And what happens is, as the groundwater goes down and down and down, at some point it just becomes impractical to actually be able to drill a hole that deep and extract water. The other problem that they're having in Phoenix is that they've been pumping so much groundwater out of the ground for so long that the ground is starting to sink. And so here's a map of what we call subsidence of the ground. So it says land surface displacement, and the numbers are in centimeters. So red means minus 15 centimeters. So this number here, that's minus 12. That means the ground has literally sunk 12 centimeters between 1996 and the year 2000, right? So in 4 years, this is how much recorded subsidence. How much did the ground sink, right? And so you see this whole area here has been sinking. And as a result of the area sinking, there are these really strange fissures opening up around Phoenix because the ground is all sinking as they suck up all this groundwater. And these big fissures have been opening up all around. So they need water, right? And they are entitled to Colorado River water. So, in fact, if you go back to Parker Dam, which is the one we just saw, there is another project, another canal that takes water from that dam, from the Colorado River, goes all across the Arizona desert and goes into Phoenix. And then, actually, about the last 10 years or so, they've extended it all the way to get into Tucson. This is how Phoenix can continue to survive in one of the hottest, driest places in the country, called the Central Arizona Project. And here's what it looks like, right? Just weird, like this artificial river going through the desert. And I like this picture because here we are in Central Arizona, and yet, oh look, we have golf courses. How could that be? And you can see the canal right next to it with all the water coming from the Colorado River. Another picture here, okay? Well, California is not done. And in fact, if you go further south, so that we've been looking at Parker Dam, we go all the way down to, there's another little tiny dam called Imperial Dam. And coming off of Imperial Dam, something called the All-American Canal. I don't know exactly who named it, but it's ironic that's right on the border with Mexico, right over here, the All-American Canal. And you see it branches up. There's a whole bunch of branches that come off of this, and there's actually hundreds of them. I just drew a few of them on here. If you look at a satellite image of this part of the world, so there's Central Valley of California, okay, and it's kind of green, and there are dams in Northern California that bring water down and irrigate a lot of the fields, plus they have a lot of wells there. And then you'll notice it gets super dry, right? This is super dry. We're in the desert here. And then notice down here, there's a blob of green there, a blob of green there. I'm going to zoom in. This blob of green right here, that's the international boundary, border right here. This is called the Imperial Valley, this and this. And if you look right there, I don't know if you can tell this or not. Yeah, these are sand dunes. And this is what it looks like. Okay, so this is a picture taken from that spot right there. Okay, this is how dry this area is supposed to be. Remember, we're in the area of the Pacific Subtropical High for a big portion of the year. Very dry, very hot. You see nothing green in this picture, right? But by bringing in water, this All-American Canal, and you can see it right there, comes right through here, and then this whole green zone is one of the richest agricultural areas in the world. Very likely, you have eaten something today that has come from this area called the Imperial Valley. And here comes the All-American Canal going through the sand dunes on its way through the desert until we get to this. You can see super dry mountains in the distance, very green fields up ahead. And all of these green fields here are being watered with Colorado River water. It's a perfect place to grow crops. It's sunny almost every day. It's warm. The soil's good. You just don't have any water. Problem solved. We've got the All-American Canal bringing in water down from the Colorado River. So that's what's happening here. And my question then is, okay, if the Colorado River comes down and crosses into Mexico and then goes and dumps into the Gulf of California, after we divert it through all these different canals and all these different dams and what have you, what's left when it crosses the border, and what's left when it goes into the Gulf of California? So I'm going to look. We're going to zoom in right in here. Here's the international border right there. This is the path of the Colorado, and I'm going to zoom in here for you. And I'm going to zoom in a little bit more. Right here, zoom in a little more. That's the Colorado River. Notice there's no river, right? You can see where people are spinning donuts out here in the dust. The Colorado River has not reached the ocean since 1983, except for a couple little exceptions to that where they released a little bit of water. So the Colorado River, 100% of the river is used up by people. So in all these different water projects we're talking about, the Colorado River is split up all these different ways. And if you remember when we started talking about this, I said that 1922 is a record wet year and nobody gets the amount of water they want. Everybody's arguing about it. None of it gets to the ocean anymore. And that ecosystem from here south all the way into Mexico, that whole ecosystem around the river completely collapsed, right? Because all that water just got turned off. So where the Colorado River has that 1922 agreement, there was a similar agreement for the Rio Grande. It's called the Rio Grande Compact. And the Rio Grande itself starts up here in Colorado, then comes down through New Mexico and forms the border between Texas and Mexico, right? And so there's 3 American states that share the river. And so there is a legal agreement as to how much each state gets from that river. And so we also have several dams along the Rio Grande River. And so if I zoom in a little bit, So here comes the Rio Grande, kind of makes this big bend as it goes into New Mexico. Here's one, Cochiti. If you're from around here, you might be familiar with Cochiti Dam. Here comes the river, and the river continues down here, and there's the earthen dam. Cochiti Dam was built in the 70s, and initially it was supposed to be a much bigger reservoir than what you see in this picture. In fact, if you look at this, it looks like it needs a lot more water in it. Partly that's the drought, partly because when they built this, they kind of screwed up. And it turns out that if you put too much water in this reservoir over here, it comes boiling out of the ground over here. And that's because they didn't study the subsurface geology correctly. So this dam, this reservoir will never get any higher really than what you see in these pictures. But people still use it. And so Cochiti Dam is up here. Albuquerque's right there. And then you go all the way down here in the southern part of the state, and you get to a couple of dams that are also pretty well known. In particular, Elephant Butte Dam. And Elephant Butte Reservoir is actually a pretty old reservoir. Today, after the Rio Grande Compact, it's essentially like a holding pond for Texas, meaning that Texas is legally entitled to a certain portion of the Rio Grande water. And we, as New Mexicans, have to be able to deliver it to them when they want. That's part of the agreement. So Elephant Butte is, the reservoir itself is water that is waiting to go to Texas. And then when they say we need 100,000 acre feet, we send it on down to them. Okay. We've been in a drought situation for a long time, and you can kind of see by the rings on this rock here that the lake level should be a lot higher than it is. In fact, it's only been like a few percent full for the last several years. Now, one of the problems is, similar to Lake Mead, here you have desert area, it's hot, it's dry, low relative humidity, lots of surface area, right? So how much are we losing in evaporation each year? A lot, right? And if we're getting in legal trouble with Texas, because if we don't have enough water to send to Texas, then we can get fined and we have to pay them, and who wants to pay Texans? So we have to have a way to prevent losing so much water. And people have been working on like, what could we do to prevent all this evaporation? And so this sounds crazy, but one idea might be to cover the entire lake with like ping pong balls. Now these are not ping pong balls, they're bigger. This is a reservoir in California where they've had a water crisis there forever, and they decided that they would cover the entire lake with these plastic balls, and it forms a layer and prevents evaporation, right? So we might have to do something like that with Elephant Butte someday. Now, here's a magazine ad. This is pretty low quality. It's the only one I can find. It says, name a great American city on a large body of water. And it shows a guy windsurfing out here. And you look at those buildings in the background. And I know it's a really crappy image, but is there anything back there you might recognize? Because this is supposed to be a picture of downtown Albuquerque. And it may seem crazy to us now, but there was a time when they were advertising people to please come here because we have so much water. Yeah, we're in a desert, but guess what? Underneath Albuquerque, huge amounts of groundwater. So much groundwater is as much as a Great Lake, much as Lake Erie, something like that. Well, back then in the 80s, they did some research and they decided that, yes, there's this huge reservoir of groundwater beneath us. Bigger, like I said, Lake Erie-sized body of water. This is something called a cross section, and so you're cutting the earth in half and you're looking at it from the side. Here's the Sandias, Northeast Heights. There's the river. Then there's West Mesa over here. So Rio Rancho's over here, right? And this has what we call a high vertical exaggeration. So what is the distance here? It's I don't know, 10 miles. But what is this distance, right? 1 mile from here to here. So it's been vertically exaggerated much more than the horizontal scale. So point is, though, they thought all of this was groundwater down here. And they thought this because they drilled a few wells and they kept finding groundwater. And they're like, oh, this is great. There's Lake Erie underneath the ground here. But then they did some more studies after they published those magazine ads. And they realized that, oh, actually, it's a pretty small amount of groundwater. And it's really, really old. Like the water down here is like 10,000 years old. It's left over from the last ice age. And what's it like under, say, Rio Rancho? Whole lot of nothing. And so all these people were moving here. Intel set up Rio Rancho and all that. And they realized, oh, wait, we don't actually have any groundwater. And the groundwater that we do have, we have to drill deeper and deeper and deeper. And our wells are well over 500 feet deep to get to groundwater. What are we going to do? So in the original 1922 compact, we are entitled to a portion of the Colorado River water, even though, as we said before, the Colorado River does not go through the state of New Mexico, but we're in the watershed. So these 3 rivers, and there's actually a whole bunch of little ones, but these 3 are the larger ones. These feed in to the San Juan, which, this is Navajo Dam here, but this is the San Juan River, and that eventually dumps into the Colorado River. And so legally, we're entitled to a portion of the Colorado River water, but we don't have to drill a hole and run a pipe all the way to the Colorado River. What we can do is we can take water out of these rivers, these tributaries that feed the Colorado River. We can take water from there. Second problem, how do we get it to Albuquerque where we need it? Well, we're on the wrong side of the Continental Divide. So here's the Continental Divide, which is green on this map. I believe it's pink on your map. So the water naturally wants to run to the west. We need it to get over here to the east. So we're going to use a trick from Colorado's book, and we're going to drill holes underneath the mountain, and we're going to drop that water into the Chama River, which is then going to flow down and dump into the Rio Grande, which is then going to take it all the way to Albuquerque. This is called the San Juan Chama Drinking Water Project. Okay, so here's those 3 rivers that dump into the San Juan, which dumps into the Colorado. We're going to put 26 miles of tunnels through the mountains and come out the other side and dump. And there's a couple little reservoirs over here along the Chama, but eventually that water gets down and joins the Rio Grande and then makes its way first through Cochiti and then eventually down to Albuquerque. So this is what it looks like on your map. I've got this red line here representing those tunnels, the San Juan Chama diversion. Okay, so it's another trans-mountain diversion. Water is supposed to land on west of the Continental Divide, but we're going to redirect it east through the divide and out the other side where these tiny little dams are. So, unlike California, we're not going to have a big long pipe that goes hundreds of miles. Unlike Arizona, we're not going to have a canal that goes hundreds of miles. What we're going to do is we're going to have tunnels through the mountain, but then we're going to use the natural rivers to take that water to Albuquerque. Here's where the water goes under the mountain into the tunnels, where it enters into the tunnels. Kind of here's where it comes out the other side, Huron Dam, and then eventually it comes all the way down the Rio Grande and it gets to Albuquerque. Does anybody want to drink water out of the Rio Grande? No, they do not. So part of this project is you also had to build a world-class water filtration system for this water. Because what's going to happen is that water comes down the Rio Grande and we just pump it out of the river, and ultimately we want to drink this. So here's where here comes the water down the Rio Grande. There's a little dam. You can't even see it. It goes up and down. It's right through here. They raise it up when they want to take water out. They lower it down when they don't. If the dam is raised and the fish are coming by and they can't get around, no problem. We got a little fish passage where they can go around the dam. And this is our water treatment facility. And if you're familiar with Albuquerque, it's kind of around Renaissance area. So there's like a Home Depot and stuff around there. Big old building. But what they're doing is they're taking all kinds of stuff out of the water and making it drinkable. And then from there, it gets pumped throughout the city. There's a second system that takes river water that's not treated, and it takes it to golf courses and parks. All right, so don't drink the water out of the sprinklers because it may be untreated river water. So this was started, this project took a long time to build, and alongside of that was this big citywide project to get people to save water. So back in the mid-90s, your average person in Albuquerque was consuming 250 gallons of water a day. Now, that's mostly outdoor watering. Okay, so a lot of this is convincing people that they don't need these big, lush green lawns. But there was a big campaign. If you lived in Albuquerque, you may remember there's lots of billboards about try to save water, try not to take long showers, et cetera, et cetera. And they got to, by 2011, they got to their goal of 150 gallons per person per day, which just still seems like a lot. If you lined up 150 gallons of water and think, I use that every single day, still seems like a lot compared to the rest of the world, but it's 100 gallons less than what we started. And so there was a campaign for that, and then we slowly switched off from the well water to the San Juan Chama water. And it wasn't immediate. They keep increasing the proportion of San Juan Chama water. So this is a couple tables of depth to the water table. 538, 542, that's how many feet down you'd have to drill to get to the water table in a couple different areas in Albuquerque. And so we see this kind of bump here, or these waves. That's the wet, dry season. And then we see about 2007 is when we start to transition over, we start shutting these wells down, and we see the water table starting to rebound. And, it's still 500 feet below the ground. It's going to take a really, really long time for that to rebound all the way to where it used to be. But point being, because we switched over the San Juan Chama water, our water tables are slowly starting to rise back up. It'll take decades for them to get back to where they used to be. So, what allows us to stay here in Albuquerque? San Juan Chama project. That's what is actually allowing us to have water every time we turn the faucets on. Every city in the Southwest has a story, right? The reason Phoenix can exist where it does, the reason Las Vegas can exist where it does, the reason Los Angeles can exist where it does, are because these very major, what we call water projects, dams and reservoirs and aqueducts and canals and tunnels through mountains and all these things. So there's this huge network of these projects that are millions and millions and billions of dollars have been invested to make this work. There's a financial cost. There's an environmental cost, right? We lost Owens Lake. We lost half of Mono Lake. The Colorado River no longer reaches the ocean. We've got dams all over the place. So there's an environmental cost for all of this as well. But this is just sort of basic introduction to the big water projects that allow us to live in the driest place in the country.